Hey guys, last lesson. So go ahead and try your warm-up. This is a great way for you to check if you're going to be ready for the final or not. This warm-up is, you should be able to do it, I guess is what I'm going to say. First one is implicit differentiation. Second one is just like chain rule and kind of multiple step derivatives. All right, so let's look at number one. Notice on number one that the x's and y's are kind of intertwined. And that's why this is implicit differentiation. So remember, anytime we do the derivative of a y, we need to add in that dy dx, okay? All right, so let's try it. So we have derivative of x squared. That's going to be 2x. Ooh. Minus. Okay, for this part, we are going to need to use product rule. So we have derivative of the first, which is 1 times the second, plus derivative of the second times the first, plus 2y dy dx equals 0. All right, and they want us to evaluate this at the point 1, 4. So that means we're just plugging in x is 1 and y is 4. So 2 times 1 minus 4 plus dy dx, since x is 1, plus 2 times 4 dy dx. And then to find the slope, we're just isolating the dy dx, since that is the slope at that point. So 2 minus 4 minus dy dx plus 8 dy dx. 2 minus 4 is negative 2. I'm going to add it to the other side. Pull out a dy dx. That's 7, so divide by 7. Done. All right, number 2, we're just doing our derivatives here. So first one, dy dx. This is kind of multiple chain rules. So remember, when you have things inside of other things, start from the outside, work your way in. And remember that you'd never want to do 2 derivatives at the same step. So here we go. So we're going to start with the derivative of natural log, which is 1 over, and we keep everything else the same, sine x squared times. Now we work our way in. So derivative of sine is cosine x squared, keep that the same, times, and then derivative of the x squared, 2x. Okay, next one, I'm going to rewrite it. Cosine of 2x to the 5th. Okay, so this is chain rule. So we start by bringing the 5 down in front, keep the inside the same, drop the 5 down to a 4. Next, we want to do the derivative of cosine. So negative sine, keep the 2x the same. And lastly, derivative of the 2x, so 2. Okay, last one on C. This one is product rule and chain rule. So we start with derivative of the first, 4x cubed times the second, plus derivative of the second times the first. Okay, and notice the 5 because the derivative of the 5x, that's part of chain rule. So derivative of e to the u is e to the u du dx. So just remember, you have to do the derivative of the exponent for that. All right, so today we're working more with the substitution method. We're going to try example 1. Notice on the bottom, we have an r cubed. On the top, we have an r squared. So that should be a hint, because remember what I told you yesterday, which was that whenever you have a power and then 1 power reduced, that's a good clue as to what your u and your du are going to be. So my u, I want to make it 1 minus r cubed. Notice I dropped the square root. The square root is going to make stuff super complicated when I do the derivative. So I just want that 1 minus r cubed. my du is going to be negative 3r squared dr. Okay, so let's look at what we have here. We have our 1 minus r cubed. That's on the bottom. Cool. On the top, we have 9r squared dr. What I have here is negative 3r squared dr. So I'm going to have to adjust that a little bit. How can I make that what I want it to be? Well, I want it to be a 9, so I'm going to multiply it by negative 3. Have to do that on both sides, though. Okay, so negative 3 du is 9r squared dr, and now that is exactly what I want for my substitution. So what that means is when I substitute, I'm going to need a negative 3 out here. That's coming from that, okay? All right, so it looks like the top of this is just du. The bottom of it is the square root of u. All right, I'm going to rewrite this. This is u to the negative 1/2 du. All right, super simple regular integral. So I'm going to add 1 to the negative half. I get positive half. I multiply by the reciprocal of that, which is 2. That's the same as dividing by 1/2, right? All right, so negative 6 u to the 1/2. Plug in my u. And I am done. Okay, let's look at example 2. So on this example, I'm going to have my u be the inside of my square root, so 2x plus 1. And I'm doing that because I know that I basically just cannot have any sort of chain rule situation. So I can't have a square root with a complicated expression underneath it. So let's just see what I get here. So I got my du is going to be 2 dx. Okay, so the problem here that I'm going to see, and we haven't seen this problem yet, is that here's my u. Okay, that's fine. Wow, those are horrible. Okay, there we go. But look at my dx. 2. What do I need? X. Okay, so that's a bit of an issue. So I'm going to show you guys a trick that we haven't done yet. Since I need an x in my integral and I do not have it, all I got out was 2 dx when I did the derivative of my u. So what I'm actually going to do is I'm going to solve for x from this equation right here. Okay, so I'm going to minus the 1, divide by the 2. And so now that actually is going to go in for the x that I have to substitute in for in the original integral. All right, notice I have this extra 2 over here, guys. So I am going to divide by 2. And my 1/2 du is going to go in for my dx. All right, let's see what happens here. So I have an extra 1/2 that's coming in. I can put that on the outside. My x is u minus 1 over 2. Here I have the square root of u. And then my dx is just my du because I already put the 1/2 outside. All right, so this may not seem like a win, right? We kind of just have something that looks just as complicated as what we started with. We just kind of switched around u's and x's. Okay, is this actually going to benefit us? The answer to that is yes, and here's why. I now have the square root as just u to the 1/2. It's a u with an exponent. Okay, watch what we're going to do. First thing we're going to do, take out this 2. So I become 1/4 on the outside. Then I'm going to rewrite this as u to the 1/2. And if you notice here, what I can do now is I can actually distribute this into my parenthesis. So 1/4 u to the 3/2 minus u to the 1/2. And now this is just regular integral. So here we go. 1/4, I get, add 1 to the 3/2, 5/2 times by the reciprocal, 2/5, minus u to the 3/2 times by the reciprocal, 2/3. And then my last step is going to be substituting back in for the u. And I'm going to distribute the 1/4 as well. So I'm going to get 1/10 2x plus 1 to the 5/2 minus 1/6. Notice I'm reducing the fraction, don't freak out, to the 3/2. All right. All right. Let's try the next. Okay, so the next one is finding the integrals of trigonometric functions. So let's look at example 3, and I actually do not know how to do the integral of tangent. I don't know what has tangent as a derivative. We've never done a derivative in calculus so far where our answer has been tangent. So I'm going to try, since we're in the u to u substitution section, what if I tried rewriting tangent as sine over cosine? And the reason why I think this is a good idea is because cosine and sine have each other as derivatives, right? So this is a good thing for us. All right, so which one do I want to make my u? Which one do I want to make my du? There is a right answer here. So if I made sine my u, my du, oops, that was supposed to be dx there. It's supposed to right here. If I made sine my u, my du would be cosine of x. Great. Here's the problem. It's on the denominator. I do not want my du in the denominator. That is a no-no. So I'm actually going to make my u cosine in this one. So my du is negative sine dx. And that's not a big deal. We'll just add a negative in when we substitute. All right, so we have a negative now, and this becomes du over u. Okay, so notice here my sine x dx. That was here, so I have a negative du going in for that. All right, integral of, I'm going to rewrite it real quick for you so it looks a little nicer. Integral of 1 over u is natural log. We know that. And now I just want to plug in. And notice you do want to do absolute value symbols because you cannot have the natural log of a negative. So whenever we have something happening like that, we want to do that. One quick thing actually before I circle this. Since it's a negative natural log, another way of writing this, do you remember what happens when we have like a natural log or a log and we have something out in front, like a coefficient, in this case a -1? We could think of this as the exponent, right? So this would actually be secant because it's 1 over cosine. Okay, so either way, but why don't you work that all the way through just to show on that one. All right, we're going to try something similar for number 4. Let me erase. Okay, number 4, we have integral of secant x dx. Oh man, if this was secant squared, we would be golden, wouldn't we? But we actually don't know something that has secant as its derivative. So on this one, we are going to use some trickery and deceit. So I'm going to rewrite this as secant x times secant x plus tan x over secant x plus tan x. Okay, so that fraction's equal to 1. So technically not breaking any rules, right? Okay, let's go ahead and distribute the secant. So I get secant squared plus secant tan over secant plus tan. All right, now it might have seemed crazy. Why did we do that? But I'm hoping you're noticing two really cool things. Number one, on the bottom I have tangent. On the top I have secant squared. Secant squared is the derivative of tangent. On the bottom I also have secant. On the top I have secant tan. Secant tan is the derivative of secant. So this is looking good for us. All right, so let's let our u be the denominator. Secant plus tan. Our du then would be derivative of secant, derivative of tan. I am going to switch the order so that it looks like the numerator. So this would be secant squared plus secant tan. All right, so now this becomes du over u, or 1 over u du, right guys? So natural log of u again. Plug back in your u. All right, so this one, bit of a stretch of coming up with that on your own. I know that one was a bit tricky. Here we have the rest of our integrals for just the single trig function. So we have tan, cotan, secant, cosecant. All of them turn out to be sort of that natural log that we saw on example 3 and 4. All right, next example. So on this one, you're going to see that we're going to use a trig identity. So we have the integral of sine squared x, and we're going to use the identity that sine squared of x is equal to 1 minus cosine 2x over 2. And the reason why this is a helpful identity to use as a substitution is because it makes the trig function a single power instead of a squared. All right, so if we're looking at this, first thing I want to do is I actually want to pull out this 2 because it's a constant. And since it's in the denominator, it comes out as a 1/2. Okay. All right, so now I want to think about what do I want to use for my u. The only reason I even need a u to u substitution on this one is because of the cosine 2x, right? We know how to do the integral of cosine of x. Cosine of 2x, we need to use a u to u substitution. So my u is going to be the 2x. My du is going to be 2 dx. And so what that means on this one is that since I don't need the 2, I'm going to divide that over. So 1/2 du is equal to dx. All right, let's sub it in. So since I have this extra 1/2, I'm going to combine that with this 1/2. It's going to become 1/4 integral of 1 minus cosine of u du. And now I'm ready to integrate. Integral of 1 is u. Integral of cosine is sine. Okay, and then the last thing I'm going to do is plug back in my u. If I want to distribute in the 1/4, I would get 1/2. There we go. Side note, on all of these, I really should be adding a plus c. Do you remember when we first started doing integrals, we would always have the plus c, because if we do the derivative and there was a constant in there, it would just disappear. So the plus c is kind of implied. You can write it. It would probably show up on a multiple choice of a test or something like that. But I've just been getting lazy and not writing it. But yeah, when you do a integral that does not have bounds, aka numbers on the integral, you need the plus c usually. So I'll put it on this one there. Okay, let's look at b. So on b, we're going to use another identity to substitute in, and again, this is just something that helps us lower the power of the trig function, and it looks like here I have a typo. I'm missing an x. Cosine squared of x dx. So this one's really similar to A. It's really the only difference is it's a plus instead of a minus. Why don't you guys pause it, try it on your own, use the steps from above, see if you can think your way through it and each step and come out with the right answer. Okay, so in the end, what you should have gotten is 1/2 x plus 1/4 sine 2x. And like I said, it's the same steps as above. The only difference was the plus instead of the minus. All right, let's look at number 6. So it says, sometimes algebraic manipulation or trying different substitutions may be necessary as seen in the following examples. So what they're basically saying on this one is that there's no obvious substitution. We have dx over e to the x plus e to the negative x. It's like, okay, well, there's no obvious way to go here. All right, so I see that I definitely have a problem in terms of having all of this on the denominator and just not being able to do the integral as is. So I'm going to show you guys a little trick on this one. I'm actually going to times the top and the bottom of this by e to the x. Okay, so on the top we get e to the x. On the bottom we get e to the 2x plus 1. Okay, so the reason that we did that is now it's just a little bit more obvious to me what I want my u to be. So I want my u to be e to the x, and my du is going to be e to the x dx. Okay, so I know this is good because when I look here, that's right here. All right, we still have a little bit of a problem because in my denominator, I don't have e to the x, I have e to the 2x, don't I? So what I'm gonna do is I'm actually going to square both sides of my u. So this gives me u squared is e to the 2x. All right, so now let's try subbing in. So I have du over u squared plus 1, or I could write it as u squared plus 1 du, like that. Does this look familiar to you at all? I hope that it does. This is the derivative of inverse tan. 1 over x squared plus 1 is the derivative of tangent of x. So this would be inverse tan of x, of u. And then I'm just plugging back in my e to the x. Okay, so we're going to put that one in the same pile as number 4 in terms of just needing a lot of experience, a lot of practice to be able to see what to do in terms of this first step, timesing by e to the x. But the more you see, the more you know. All right, last one, number 7. We're going to do this in 2 ways. They're giving us 2 different u's to use. So we're going to do them both ways, and we should get the same answer. So I want you to split this into 2 sections. Okay. First one, they want us to use a u of z squared plus 1. My du is going to be 2z dz. Wow, that works out perfectly. Look at the numerator, 2z dz. So this is integral of du over u to the 1/3. I'm writing it as a exponent. All right, rewrite it. U to the negative 1/3 du. Okay, integral, add 1 to the negative 1/3. I get positive 2/3 times by the reciprocal, 3/2. Plug back in for your u. You guys are seeing why I crossed my z's. They're like, my 2's and my z's are very similar. All right, plus c. Okay, let's try it the other way. And remember, hopefully we're going to be getting the same answer. All right, here we go. On this one, they want us to use our u as the cubed root of z squared plus 1. All right, now, if I were to do the derivative of this, I would need to use chain rule, right? The 1/3 would come down in front. I would minus 1. Get negative 2/3 as my exponent times by the derivative of the inside, 2z. Kind of a mess. So actually what I'm going to do is I'm going to cube my u. Okay, so if I cube my u, the cube root cancels and I get z squared plus 1. All right, so now let's do the derivative. 3u squared du is equal to 2z dz. All right, notice the 2z dz is the top. So this is going to give me 3u squared du. And then on the bottom is just plain u, because that's what I made my u, was the cubed root of z squared plus 1. All right, I can reduce this. I have a u squared on the top, I have a u on the bottom. So this gives me 3u du. Add 1, divide by 2, plug back in. Now, this is u squared, but remember what my u was? It had a 1/3, so I'm going to get 2/3. And I get the same answer. So just showing you guys, there's multiple ways to do these. I would much prefer the first way. I think it's much less complicated. You don't have to figure out to do the u cubed and all that, but it's nice to see different ways because someday you might have to use a different way and you want to know how. All right, homework. You have these 6 problems. And let me know if you guys need any help. Notice on number 1, I'm asking you to do 2 different u's, just like we just did in the notes. Okay? All right. Talk to you guys.